In Lecture 8, we're going to start to learn how to create maps and also put data on maps. So Lecture 8 is going to be really fun, which is probably going to be the most interesting lecture over the whole course, given that you're probably struggling in the program control and NumPy arrays, etc. But today's lecture is going to be fun. So in Lecture 7, we learned two-dimensional NumPy arrays, and if you learned how to create those two-dimensional NumPy arrays using the same functions as the 1D arrays, and we also tried to do index slicing of 2D arrays to generate one-dimensional arrays. And we also learned two basic functions provided by NumPy, load.txt and gen_from_txt, to load data from files, and then we can make further analysis. And also we did some basic techniques on how to visualize your data based on the files. So lecture 8, we will be creating maps. That's all for today. And in the end, we will show how to plot spatial data points on your maps so you have a much better idea about what those data are telling you. So first of all, what is a map? So a map is basically a projection tries to represent something that is 3D onto a 2D medium, because we're living on the Earth, which is not flat. So we're trying to project something 3D to a 2D plane. It's very convenient. You can see everything, but make sure you understand that all the maps are distorted some way, right? So this is, for example, an example of a world map. You've probably seen a lot. These are coastlines, right? You see the North America, Asia, Africa, right? So the idea about today's lecture will be going to be learn how to make simple maps like this using Python, and the module is called BaseMap. Right, so how to make maps in Python? So there are many ways to make maps in Python, but in this course, we're going to use one very popular tool, which is in Matplotlib's BaseMap module. So the first thing we need to do is to install base module in Anaconda. Why do we need to install BaseMap? Because you remember that you have used the modules like Math, NumPy, Matplotlib, which you did not need to install them at all. But why do we need to install BaseMap? Because BaseMap is not a default module installed, but while NumPy, Math, and Matplotlib, these are already installed for you by Python. So you don't need to do that. All right, so how are we going to install the BaseMap? Which is really straightforward. So if you open Anaconda and click Environments, the tab here, and you'll get into a page like this, right? So in this list, which with these green ticks, and these are the modules installed, right? So you can see that if you select this one and select installed, and that's all the installed modules default for you. And you can see that NumPy is already installed here, right? But if you scroll down or scroll up, and you will see that the BaseMap module is not installed, which means that it's not a default module for most of the Anaconda users, right? So how are we going to do this? So it's very straightforward. And usually what we do is that you select this window, and instead of choosing installed, you choose not installed. And by doing this, and you type in here in the search packages, type in BaseMap. So once you type in BaseMap, it's going to show up what kind of BaseMap that's there for you to use. And now this is the one on my computer, and now it says there's BaseMap, and description says plot on map projections using Matplotlib, and the version is 1.2.0. So if you tick this little sign and to choose that BaseMap, that's what I want, and then you click apply, and that's done. And Python is going to go to the library and install BaseMap for you. That's quite straightforward. All right, so the next step is to wait and let Anaconda does its job, right? So it's going to install and wait for maybe a couple of minutes, and then the module is going to be installed. So once it's installed, and how are we going to use it? So to use the module, which is the same as how you use other modules, the first thing you need to do is to import the module, right? So for example, so the syntax goes like, if you still remember, import numpy and matplotlib plt, and also so for the base map, and we use this from npl toolkits.basemap import basemap, right? So the module is called basemap. So now we can use all the functions in the basemap, which is it's a very nice convenient tool. So some users may have problem with the path for the PyProject library. So if this import module doesn't work for you on your computer, you might want to try the following syntax with 2 additional lines of code. So import OS and OS environment, and set the environment of that to be there. So this might not be needed. So when you finish install the base map module and try to use this first. If it doesn't work, and let's try something like that, and I'll see how things work. Because on Windows and Mac computers, that sometimes they might be slightly different, right? Okay, so this is the how you load the base map module. So now let's create maps. So the basic syntax of creating maps using the basemap function or module is like this. So m equals to basemap parenthesis projection, which is required, and options, which tells the basemap function how we're going to specify our map. And then m dot draw coastlines. So draw coastlines is a function of the map project here, right? So how does this work? So first of all, M is an object of the basemap class. Remember that everything is a class in Python. Like the one-dimensional array you worked with NumPy, that's an n-dimensional ND array class, right? So M is a basemap class, and you can just regard it as a map with the name M. So basemap is a function that creates a map object. So basemap is a function that creates a map for you. And projection, which is an input which is required, tells the basemap what kind of maps do you want. Do I want a globe? Do I want a square map? Or do I want some weird projection? So there are lots of options. And the options here are lots of input arguments specifying the style, the label, the color, etc. of the map. And draw a coastline function, put on coastline so you can see the shape of the continents, which is basically the maps, right? So that's quite straightforward. Now let's take a look at one of the most popular projection, which is called the Mercator projection for the word map, Merc. All right, so how are we going to do it? So first of all, plt.figure. So I create a figure. I give a size 2015, which means I want a relatively large sized figure, right? So remember that how we create map. So m equals to base map, projection equals to merc, MERC, which is Mercator, right? So by doing this, I'm telling you that I want a 2D projection, square projection of the map we usually see. And there are other options we will go through later. And then after we call the basemap function, I've created a map object here, or map class here. So I use the function draw coastline, which is m dot draw coastline, and to put on the coastlines. And if you don't specify anything, it's going to be black. And then plt.show shows the map. So this is what I get. So that simple 3 lines of simple codes give you such a complicated nice map here. All right, so now let's take a look at these options. Right, for example, this is a lower left corner latitude. So it's a little bit awkward, but idea is it's saying that this is a latitude on the lower side of the map. And similarly, and you can see that this is upper right corner latitude, which is the latitude up here. So in this example code, I set them both to be -70 and 70 degrees. So they're symmetric between the two hemispheres. So the same idea, this is a lower left corner longitude. So I'm saying what's the longitude here on this side? So this is 100 minus 180. And the same idea, the other one is the upper right corner longitude, which is 180 degrees. So this is how I create a map and specify the region of the map I want to see, right? So that's quite straightforward. So let's just give you a simple idea about why the maps are distorted. So there are different ways of projecting things. So if you regard this as the Earth, so each line, the angle down here is basically the latitude, right? So because the Earth is three-dimensional and I want to put three-dimensional information on a 2D plot, which especially a square plot. So what I do is that for each latitude, I do this horizontal cut and put the information along this latitude in the same region based on the longitude is the same, but latitude is taken by this projection along this line. So you can see that as this latitude goes up to from 15 degrees, 30 degrees to 60 degrees, to 75 degrees, and the spatial extension between this mapping point to the equator becomes larger and larger. So even though my latitude is increasing uh, uniformly, but you can see that distance between these lines are not. So that's how you can see the distortion of the map area as the latitude go to higher, which is very nice example to understand is you can see Iceland. So if you remember that, we'll go back to that later, right? So Mercator projection is something similar to such a cylindrical projection, but it's not that extreme, right? So Mercator projection goes like a cylindrical, but to somehow we use a mathematical function to map these lines, squeeze them slightly closer to each other instead of doing purely cylindrical projection, right? So this way you get this distortion, but the distortion is still there, and there's more distortion at higher latitudes. And you can see, for example, Iceland, right? So for example, look at this map. So this is Iceland, Greenland, Iceland, and you can see that Iceland is about the same size as UK, which is ridiculous, right? Because Iceland, you can probably drive around the island within like 8-10 hours, but you can apparently cannot do that. So this is why when you go higher latitude, the area of the map is distorted, right? So this map is based on the same one based on the simple map we created, but the difference between this one and the first one is that now we have labels to show where are those latitudes in this case, right? So you can see how to do the labels, and the function is called draw parallels and draw meridians, right? So first of all, draw parallels. So if we do m dot draw parallels, it's going to draw these parallel lines, which are the latitudes in this case. So what we wanted is that we started from 90 degrees to minus 90 degrees to plus 91 degrees and separated by every 30 degrees. So that's why I got 0, 30, 60, 90, and all the way down there, right? So the same idea as is to draw the meridians. So draw the meridians will go through these vertical lines, which are the longitudes, right? So what I want from my minus 180 degrees to plus 181 degrees and 60 separated by every 60 degrees. So think about this, why I do 181 instead of 180, because 181 is excluded in this case. It's a range, if you still remember this a range function. All right, so the next thing, you use that to where to put those labels, right? So if I do the labels in here, instead of putting the labels with numbers, what I do is here, so the labels option tells you whether I put labels on each line. So the first one goes on the left hand side, and the next one goes on the right hand side. But so these others are false, because if you turn on, there will be labels everywhere, right? So you can try that. And for the meridians, the label options are set as true for the last two options. So these are in the horizontal directions. So that's how we put on the map and use all these labels. So these are basically the codes that you can just use, and these example codes are included in the lecture 8 Jupyter Notebook file. All right, so you can also change the colors of the labels, because sometimes you see different maps with different colors, which is really easy to do. So we use another function. So after we introduced all these functions, the next one is fill continents. So you can tell from the function name, it's going to fill the continents and what color, and you can specify as an input in here, its color equals to green. So And also you can specify the boundary outside the countries, what's the color, and it's actually light blue. So if you say draw map boundary field color equals light blue, so the outside the continents it'll be filled with light blue. So this is basically the new map you can see, and all the continents are green and the oceans are in light blue, which is fairly nice. So on the other hand, so we've learned how to create these maps, right? They're very nice, but the nice thing about maps, that unless you're just trying to use a map to navigate, but for earth science, the point of creating these maps is that we want to put data points on the maps, right? So how to do that? For example, you have maps, and then the map is basically a two-dimensional projection of numbers, right? So these are latitudes, that's longitudes, these are latitudes. So let's see how we can put the location of Hong Kong on this map we just created, right? So first of all, we define two variables. One is Hong Kong lat, which is about 22 degrees, and the next one's Hong Kong long, which is 114 degrees. That's the longitude and latitude of the city Hong Kong here. So if you just do plot Hong Kong lat and Hong Kong long, you're not going to get anything. So what's wrong with that? Is because these are longitude and latitudes, while when these maps are created, and although those labels saying these are longitudes, latitudes, but the data points behind these map, they're not in latitudes and longitudes. And their actual numbers are much, much larger than these longitudes and latitudes. So what we do is that we create these longitudes and latitudes, and we use the map coordinates, and we map those longitudes and latitudes to the map coordinates, x, y. So how we do it, we do m, as we can put in two functions. Remember that m is the name of my map, and I put in the longitude and latitude and map them to x and y. Now x and y are the location of Hong Kong on my map in the map coordinates. All right, so by doing that, now we can do plot x and y and use a star and with a much larger marker size, and then I put on text. So x and y, so the text function is putting some text on the map at the same location and x and y, and that's saying the font size is much larger. And then if you do that, and you can see there's a little star here and saying Hong Kong there, right? So now remember that, let's go through this again. So once you create a map, which is called M, and if you want to map something, put something on your map, and you need two steps. First is you take your latitude, longitude locations and convert them to map coordinates using this syntax. So xy equals to m, the longitude and latitude in degrees. And next is use the plot function or scatter function or whatever function you want, and to put the data on your map. So here is a nice example showing the use of the Makita projection of global GPS TEC maps. So TEC means total electron content. So that's actually the total number of electrons above the atmosphere and viewing from top, right? So you can see that this is the Makita projection of the global map with all these continents, and the colors showing you the number of the TEC units, right? So red is 5, blue is -5, and this is actually a logarithm scale. So we can see that in this case, so this is also a nice animation from MIT Haystack, and you can see that the changes of these electron structures. So this is the northern light, so that's the northern light high energy electron precipitation from the space, and these regions, and you can see the increase of the electrons, and this is the southern light, that's the southern light. So this projection shows very nicely on the dynamics of the change of the electron content over the hemisphere or over the whole globe, right? So this is a very useful usage of the Makita projection, and it's used a lot, which is probably the most popular map projection in lots of earth science applications. So the Mercator projection is a very nice way to create two-dimensional maps for the whole globe. But the problem is that it distorts the map areas at high latitudes. Right? So there are other ways to do the maps in an interesting way, and one thing you can see is called the orthographic projection, which gives you something like a 3D sphere in this way. So how are we going to do this? Remember that the projection option tells BaseMap what kind of maps I want. So to generate a map like this, and we use the option called projection equals to ortho, ORTHO. So there are two uh, options you wanted to do. One is longitude 0, one is latitude 0. So longitude 0, latitude 0 tells you where is the center of the map. So in this case, I'll see we chose a longitude 0 to be 100 degrees, so it's somewhere down here. And latitude 0 is 30 degrees, so it's exactly right here. So which means I'm viewing this map from somewhere up in the space and looking at this point down. So this is how I generate a map like this. So everything else is the same. Draw parallels, we've learned how to do that, and draw meridians and how to use that, and draw country boundary, and with that, and we filled the continent with orange, and we filled the ocean with light blue. So this is how we use the change the map to be orthographic mapping. And the same idea, if you remember that how we put the location of Hong Kong on this map is that we get the latitude and longitude of Hong Kong in degrees, and then we map the degrees into the map coordinates using m, the hk long, hk lat equals to xy. So this step is very, very important. So whenever you want to put data on your map, make sure you don't forget to do the mapping step, right? So after we do the mapping step, now x and y are the locations of Hong Kong on this map in the map coordinates. Now we can plot an xy and using whatever labels, markers, size of the markers you want, and we use the text function to put the location of the explanation of Hong Kong on the map. And then so this is basically the same code, but we change the projection to ortho. So in this case, you get something looks like a 3D globe. But problem of this is that instead of you have all the globe, you only have one side of it. So you only have a part of the information, right? So this is also a very popular usage of map projection we use. For example, in atmospheric simulations, we use that at all. So a lot. So this is a nice animation that I did a while ago, showing the air temperature at 400 kilometers altitude, which is the upper atmosphere, and during a geomagnetic storm. So you can see that the colors are the temperature of the air, and then dark is very, very cold, and the blue is about a thousand degrees Kelvin. It's very high, but this is a thermosphere. So the thermosphere is the hottest layer of the atmosphere, right? So if I let it go, and you can see that it's that dynamic evolution of showing the changing of the temperature, and you can see that the lower the polar region gets heated constantly, and then these structures going down to the low latitudes because of the circulation of the atmosphere. So these are called the traveling atmospheric disturbances, these structures, right? So how's this created? So I create a map at each time step, and then at each time step, my viewing point is changing because the Earth is rotating. So at each different time step, I change the view and also change the data and given each different data point with different colors. So these are filled contours or pseudo color plots, and we will learn that later. Right. So there's another popular projection that we use a lot in papers, publications, presentations. It's called the hammer. So the hammer projection is a compromise between the Mercator projection, which shows very distorted polar region but has everything, and the orthographic projection, which is not distorted but only have half of the information, right? So the hammer projection looks like a ellipse, and you can see that it's less distorted in the area, but the shape of the structure is more distorted towards the north and south when you look at the boundary of the maps. So how to create a map like this? So we use exactly the same code, but the only thing we did is that we changed the projection in base map to be hammer, right here. And there's only one parameter needed for a hammer projection is where is the center longitude, because the latitude is always 0. Right? We're always starting from looking at the equator. So now we choose minus 200 degrees, and then the center latitude is down here. So if you choose the center longitude of where Hong Kong is, and then this point will be shifted down here, and you get a different mapping of the Earth. Right? So everything else is the same. So remember that go through again, hammer projection, you need to change this to hammer, and then you give the center longitude where you want to view the map, which is quite straightforward. All right. So, for example, this kind of map is used a lot to visualize the changes of the globe, especially atmospheres and things. So, this is a nice example showing you the changes in the ionosphere and the neutral atmosphere conditions during a solar eclipse in the 2017, which is called the Great North America Solar Eclipse. Right. So you can see this is the path of the solar totality, and then this is the point of where the totality is, and then the color shows the mask of the solar radiation. So you can see there's a decrease in electron density, increase in the winds, and everything. But the point here is that you can see this kind of map give you a global picture of what the features look like, although the sides will be slightly distorted. Right, so I'm now going to go into this, and this is the same simulation from the event that we did, and you can see that during the solar eclipse and the changes in the total electron content, and because of the masking effect of the sun, so the sun is masked by the moon, and then there's less ionization from the sun, so you can see the electron density drops and moving with the location of the moon. So that's the totality. So this is basically a simulation of a global event of the solar eclipse in the atmosphere. And then as time goes on, you can see that neutral temperature changes, and the neutral wind changes, and the winds coming from the northern hemisphere and turning directions. That's because of the Coriolis effect. And then you can see all these winds in the vertical structure, but this is just a nice example showing you how to use a hammer projection like this. So don't worry if you don't understand the details. The point is that you can create nice maps like this. This is just an example. All right, so so now we've learned 3 types of mapping. One is Mercator, one is orthographic, the other one is hammer. So all of them are more or less global mappings, right? So sometimes we don't want to show global mappings, we just want a part of the map. So now this is a very popular one. It's called Lambert Conformal Conic Projections. It's LCC, right? So LCC is slightly more complicated with more options down here. So the first thing to change is that to change the projection in base map equals to LCC. And now I need to change the corner latitudes, longitudes, and lower left, upper right, longitudes and latitudes. And I also need to change the view where I want to center it. And resolution is an option that how much detail I want on my map. That depends on the data sets of your map structure. Right. So after doing that, and everything else is the same. So we've learned how to draw coastlines and draw parallels, draw meridians, and fill continents, fill the ocean, and also draw countries, and also put the latitude and longitude of Hong Kong on map. And make sure I'm gonna remind you this again. Make sure you map the Hong Kong longitude and latitude to the map coordinates using this syntax. So this is very important because lots of times students will forget to do the mapping while plotting these locations directly on the map and has nothing, right? So by doing this, what I get is a map like this. So you can see that though this is the same. It looks like a orthographic, but it's actually a localized mapping. So in this way, you can see that we've created the Southeast Asia, East Asia mostly, and we put on the contours for the countries, And also we have put on the location where Hong Kong is. And you can see these options used down here is LCC and all these longitude, latitude. So these four numbers will be the corners of these four locations where we want those longitudes, latitudes are. And we filled the countries with orange, and we filled the ocean with light blue, and we draw the countries with black lines. So that's a very interesting local map that you can do. All right, so if you're gonna go more and more, and you can try other options. For example, if you want to go fancy, and you can use this NASA uh, color bar, which is called NASA Blue Marble color bar. And then if you do M after you created everything, and we do M dot blue marble, and it's gonna change the color of your map based on the altitude. And then it's the ocean, it's dark, and it's higher altitude, it becomes white, looks like snow. So this color is not real. It's not telling you the vegetation at all. It's just based on the altitude, but it looks like Earth, right? So you can see this is good NASA Blue Marble. And also there's another one called eTopo. So you can see that it's similar to the Blue Marble, but with more variations in the color. But in this way, then you can see this is very looks like a very complicated map with different changes in the altitudes and other information. Now let's do some science with the mapping techniques you just learned. All right, so record the earthquake datasets we looked at yesterday, and we were able to plot those locations of earthquakes on a longitude latitude figure that give the following Cartesian plot like this, right? So for example, let's go through this again. So we use the load.txt function to load the data, which is a CSV file, and remember that the data points are separated by comma. So the delimiter here is comma. And then we know that the first column is latitude, second column is longitude, the third column is depth, and the fourth column is magnitude of those earthquakes, right? So we create a map, and we do a scatter plot plotting the longitude and latitude, and we label this longitude, latitude, and this is the figure that we get, right? So everything's correct, right? But does these plot make sense? Like, what can you see from these figures, right? At least I can't, because I'm not a geologist in this way, so I don't know what does those points mean. So now let's see what a map can help with that. All right, so this code generates this following picture showing where those earthquakes are located on a world map, right? So this makes much more sense now. All right, so how do we get this? And it's quite similar. So first thing is we load the data using the load.txt function, and pay attention to the option delimiter and file name and delimiter. And then we slice the two-dimensional array into 1D arrays that has information of latitude, longitude, depth, and magnitude. All right. So now what we do is that we first create a figure, and then we create a map. So this information, we use that. Remember that we use a Mercator projection with minus 60 degrees to positive 60 degrees, 160 degrees here, and minus 100 degrees here, 200 degrees down there, right? So we put Africa in the center of the map, and we put on the latitude, the longitude labels, and fill with colors. So this is the third step to create maps. So all right, so once maps are created, all right, so we now have the locations of the earthquakes. Remember that? So these locations are stored in the array long and lat. So each pair of long and lat gives you one location of the earthquake. So can we just do plt.plot long lat on the map? Of course you can, but you won't get anything. You can try that. So the problem here, again, I'm going to emphasize this again, because longitude, latitude, they're locations in degrees. They're not in the map coordinates. The map coordinates are not necessary in degrees. So what we need to do is that we need to map these 1D NumPy arrays, long and lat, into the map coordinates by using this function m, long lat. And then we give these mapped coordinates to variables called x and y. So by doing this, and we use a scatter plot plotting x, y, and we show the plot, and this is what you get, right? So this makes a lot of sense, right? You can see lots of earthquakes happens on the boundary of the plates, tectonic plates, and here lots of here in Japan, here in the South Asia, and also on the west coast of the U.S. and South America, and all these in the mid of the Atlantic Ocean. So that basically tells you that these earthquakes happens on the boundary of the lots of the plates, and that's one thing that people are learning on plate tectonics, right? So I'm not an expert, so I'm not going down in detail there. But the point here is that with the help of those maps, and you can clearly see what's going on in your data set. Before, we just get a bunch of points. Now we have more information, which is very nice, right? So this is extremely useful when you're trying to visualize the track of a hurricane and a typhoon, etc. And you probably see that a lot, right? Okay, so last one, I'm gonna say this again. When you're trying to map data, plot data on your map, don't forget to map your longitude, latitude to a map coordinate. Never forget to do that. If you don't do that, you'll probably not get anything. All right, so let's make some maps. First, install the base map module in Anaconda and then make maps.